California. So it's my pleasure to have the last talk of today. So Nima will talk about scattering amplitudes and Clusterhedra in Kinematic Space. Please.
All right, I'd really like to thank the organizers again for putting together this really cool meeting. I'm going to be talking about work that builds on and is related to a lot of the work you've heard from my other collaborators earlier today, Song, Thomas, and Mark. But since they talked about all the stuff, and there's been a number of other beautiful talks on it, I thought I would talk about different work in progress with Hadley Frost, Pierre Plamondon, Hugh Thomas, and Giulio Salvatore. And let me begin with the picture that I began essentially every talks I've given at Amplitudes meetings for the past 10 years. The large overarching question is that scattering amplitudes are things that are measured at infinity. There's a normal picture of what gives rise to the scattering amplitudes, which is space-time processes, local space-time processes, and unitary evolution in Hilbert space. But we have lots of reasons to look for a different question, and a different question that naturally lives in the kinematic space of the on-shell data that labels the scattering process. A natural mathematical question to which the amplitude is the answer. And there are lots of reasons to be looking for this, but perhaps the sort of, to me, the most compelling one is that there's so many miraculous structures in amplitudes that are hidden by making manifest the usual rules of locality and unitarity. And if we perhaps understand what these natural questions are in kinematic space, it could give us some deeper insight into what the ultimate origin of space-time and quantum mechanics might actually be. Part of the idea here is that the question that we're asking is actually in kinematic space, and that a priori it's not so obvious what to do in kinematic space, because kinematic space seems like naively like a pretty dull space. So for example, if we talk about planar n equals 4 super Yang-Mills, we've already seen a few ways of thinking about what the kinematic space is. If we use momentum twistor variables, it's just n 4-dimensional vectors. If we use spinor helicity variables, it's also n 4-dimensional vectors with the lambdas and lambda tildes on the support of momentum conservation. And very naively, it's not obvious what to do there. It seems like a very dull and boring space. What kind of question could you ask on this space, which has all the richness and complexity of a scattering amplitude? And what we've seen over the past 10 years is that there's some important, a tiny bit of extra structure on this space, a notion of ordering, and also a notion of positivity. It puts just enough structure in this space in order to be able to yield remarkably, and to be able to ask questions whose answer is all the richness and complexity of scattering amplitudes. And really seeing this in kinematic space, in the space of the momentum twistor variables at the level of the integrand, where you also add a bunch of variables for the loop integrations, was first seen in the context of this topological or winding number definition of the amplitude in kinematic space that also introduced the sort of idea that we should think about the amplitude as a form. Now we've heard, especially beautifully in Mark's talk, that if we forget about, if we just try to think non-perturbatively about the full amplitude, then we should maybe be thinking about some analog of this configuration space, which opens up these issues of trying to tame this infinity that we run into with trying to compactify this space in a natural way associated with the infinities in the corresponding cluster algebra. But anyway, that's the kinematic space for planar n equals 4 super Yang-Mills is the space of n 4-dimensional vectors with an ordering, and then some notion of positivity puts a lot of structure on it that allows us to, in a sense, totally determine what the integrand is, at least find the question that determines the integrand. And now we have some candidates for moving forward with a notion of what a non-perturbative geometry might be, although there's a long way to go to figure out precisely what the question is that would yield the amplitude. So instead, since that's been talked about, instead what I'll talk about is what the analogous structures are in a much simpler setting, naively much simpler setting of just the biadjoint scalar theory. So there's no supersymmetry, no obvious integrability, none of this fancy schmancy stuff going on. But we're going to take the same attitude and see how we can find what the kinematic space is for this theory and find a natural question in the space that gives us the amplitude. So let's begin with the story at tree level, and let's think about what the actual kinematic space is. So I'm going to imagine that I'm just talking about the planar tree diagrams here. So we could draw the cubic diagram, or I could draw the dual of the diagram that looks like the triangulation of an n-gon. So Feynman diagrams are dual to just triangulations of an n-gon for endpoint scattering, and the natural variables are not directly the Mandelstam variables, but something else, which is also a basis for all the Mandelstam variables, which are the propagators that show up in these cubic diagrams, or the distance between 2 points in this null polygon square. So our kinematic space naively is just a space of xij, which is equal to xji, where the edges of these polygon are null. So xi plus 1 is 0. That's our kinematic space. Now, what are some clues that there's something interesting going on that's not captured by ordinary Feynman diagrams? Well, one famous clue by now is that the set of all triangulations are related to each other in an interesting way, that it's non-trivial that we can think about this, the set of all triangulations here, or we can think of each vertex here as being a cubic diagram with a triangulation of a polygon, but they're actually related to each other in an interesting way, and they can be thought of as the vertices, just combinatorially, the vertices of a polytope, where we think about the faces of the polytope as being the first factorization channel, or just the triangulation with one chord, the edges as being the next finer triangulation with 2 chords or 2 factorizations, and finally the vertices as being 3 factorizations, or just the cubic graphs as in this example. This is a non-trivial fact that's not manifest in how we normally think about field theory. Why should it be that the combinatorics of the way the poles come together is polytopal like this? So that's one indication that there's something to be understood. Another indication is that there's actually a hidden symmetry associated with this, with even these incredibly simple amplitudes. And to see the hidden symmetry, we actually have to think, as we've seen earlier, in other contexts, we have to think about the amplitude as a form instead of as a function. So let's say at 4 points, instead of thinking about 1 over x13 plus 1 over x24, we think about this form, d log x13 and d log x24 associated with the 2 channels. And now comes the little bit of magic, is that we're supposed to actually put a minus sign here, not a plus sign, a minus sign, in order for this form to be d log of x13 over x24. And what's important about that is that with this choice, the form is actually really a function only of the ratios of the variables rather than the variables themselves. In other words, it's invariant under a projective transformation where I just do a local rescaling, xij goes to alpha of x, xij, which means that d log x for any xij gets shifted by an amount d log alpha. Now, in this case, it was trivial that I could choose a minus sign to make it happen, but in general, this is very non-trivial. If you try to do this at n points, in order for the coefficient of d log alpha to vanish in the projective variation, for every subset of poles with n minus 4 propagators, it sort of corresponds to a penultimate factorization before we get all the way down to cubic diagrams, there's a piece in the variation of the form that's proportional to all the d logs of the variables in diagrams like this, and every one of them has to vanish. There are many more equations than unknown signs, but it's remarkable that the signs can be chosen so that this form is projected. So this projective invariance of the form is hidden. It's not true of one diagram at a time. It's only true of the sum of all the diagrams together. And it's an analog of the dual conformal invariance in n equals 4 super Yang mills. So that's one fact. Another fact is that starting from this form, we can actually pull back to determine the amplitude and to get the actual scalar amplitude. And so to do it, for example, at 4 points, there's a 1 form, and you have to pull it back to this one-dimensional subspace, x13 plus x24 equals a constant. And you see it's possible to find this subspace such that pulled back to the subspace, the form just becomes the volume form on the subspace times just the sum of the 2 diagrams. In other words, with a plus sign. The signs all go away, and I just get the amplitude. And in general, the AVHY description of the phi cubed amplitudes and the corresponding associahedron and so on that Song alluded to gives us a subspace where this magic happens. You pull it back to the subspace, all the signs go away, you just get the amplitude with all plus signs. So the form is projectively invariant, and it's possible to find the subspace on which we get the actual amplitude. Okay, so that's some of the clues that there's something going on. But now let's go to our basic question. We want to go to the kinematic space, and in kinematic space, find a question whose answer is the amplitude. And what could that question be? Because the kinematic space seems incredibly boring. It's just a space of all these xij's. But let's actually just begin by drawing the Xij. So here's a picture for a 7-point scattering, and I've just drawn here x13, and then I've simply translated all the indices according to the obvious cyclic invariance of the problem. So 13, 14, 15, 16, and 17. Remember, at 7 points, at any number of points, I plus 1, xi plus 1 is 0. So all these things on this side, on one boundary and the other boundary, all vanish. All the non-zero variables are in the middle. And already you see there's kind of an interesting structure here, that just drawing the variables is naturally represented in this strip with 2 boundaries. And I'm going to suggestively call this direction in the strip time and this direction space. We're going to be seeing some causal structure in this kinematic space-time. This is going to be a big part of the story, but already here you see that there's some interesting Mobius identification. We have 1, 3 here, for example, and 3, 1 there. So that's our xij's identified with xji. So it has an interesting identification. But the really crucial point, and the reason why the time-space labeling here makes sense, is that there's something important about whether compatible or incompatible chords or factorization channels, how they're represented here. If I take 2 chords in the polygons that cross, so the corresponding poles are incompatible, that's reflected in a very beautiful way in this sort of space-time, that if I have the chord ij and it crosses kl, then all of the natural chords in this picture, ij, ik, kl, and ij, the 2 crossing chords are actually the past and future corners of a causal diamond that fits in this quote-unquote kinematic space-time. So that's our first sort of hint that there's something good about thinking about this kinematic space-time in terms of causal structure and time and space. So here are some pictures. In order to actually cover all the variables once and only once, we have to take a chunk out of this kinematical space-time, and there are various ways of taking a chunk out. So here's one that I'll use a few times in the next slides. This is just a way of choosing out of this entire strip a set of variables where I have xij but not xji. So here's 1, 3 is in here, but 3, 1 is not. So everything is chosen once and only once. Okay, so that's our kinematic space-time. And now we have to ask a question in this kinematic space-time. And I spoke about this at Amplitudes last year, and then the paper came out in December, so I'll be a little brief here. But the question we ask is we solve the wave equation. We ask for the solutions of the wave equation, but with some positivity property, that we ask the source of the wave equation to be positive, and we ask that the solution itself stay positive. And a crucial feature of the wave equation is it's associated with a Gauss law, that if you give it a causal diamond, the solution at the past plus future minus left minus right is given by the total charge inside that causal diamond. We're going to be seeing this kind of relation x plus x minus x a lot in the next in the rest of this talk. Now, this is what I talked about last year, and is that if we look at these positive solutions of the wave equation and we just sample at a finite number of points in this diamond, then demanding that the solutions stay positive forces the x's, let's say the x's on this past boundary that determine everything inside, it forces the x's to lie inside a polytope. That's in fact exactly the sort of ADHY construction of the icosahedron directly in kinematic space. So the question we ask, so our kinematic space is this interesting strip with this interesting causal structure. The question we ask is the wave equation, and the amplitude or the form is completely determined by the requirement that when pulled back to the solution of the wave equation, it yields the canonical form for this corresponding icosahedron. All right, now all of that is said in a way where the word cluster algebra didn't make an appearance, but cluster algebras are sort of crucially behind all of this. And so now I want to spend the next few minutes telling you about the connection between the sort of simple picture of a kinematic space and some deeper cluster structure behind it, so that we understand the relationship in this simple setting before we generalize it and move it forward. So first, some very quick cluster algebra basics. The cluster algebra is associated with starting with any quiver. So here is just a quiver is a graph with oriented arrows, and we can build a different quiver by mutating at a vertex. And there's some simple rules for the mutation. You reverse all the arrows at a vertex. If before you reverse the arrows, you could have gone from A to V and V to B, you want to remember that. So you add an arrow from A to B and you delete all bubbles. Okay, so that's just a picture at the level of changing the quiver. There's also an algebra, so there's variables associated with all the vertices. And there's this nonlinear relationship that the product of the old and the new variable at the vertex is given by the sum of the product of the variables coming into the vertex plus the ones going out of the vertex. Important for us is also going to be a so-called tropicalized version. We've heard that word a lot earlier today, but a tropicalized version of these relations that for my purpose just means here that instead of taking this nonlinear relation, I'm going to look at a pair of linear relations. Now the variables will be capitalized, will be capital XV plus capital XV prime minus either the sum of the variables going in or the sum of the variables going out. And for the moment, I'm just sort of thinking of these as, I might want to set them equal to 0. I'll also just think about these as just a linear function of these capital X variables that I can also associate with all the vertices. All right, very important class of cluster algebras are associated with triangulations of surfaces. So that was in fact one of the motivations for the rules of these quiver mutations and so on, is that if I start with a surface like a triangulation of a polygon, then in this simple way, there's a canonical way of associating a quiver with it, with a triangulation, just by putting dots on the inside of all the triangles and drawing these oriented lines inside each one of the triangles of the triangulation. And this way produces a quiver. And also there's a beautiful interpretation of the mutation formula, simply skein relation. So if you're given any sort of curve on the surface, the formula just says that the product of the old and the new variable is what you get by undoing the crossing curves. Any two crossing curves and any two curves that cross exactly once have a mutation, and we have a formula that's very familiar here from the skein relations. Now, a very important part of the story of cluster algebras is its canonical way of labeling cluster variables instead of rather complicated functions of the initial seed variables. We can also label them as certain vectors that are known as g-vectors. And this depends on your choice of initial cluster. And there are lots of ways of talking about them, but for my purposes, this is what's going to be important about them. So if you have an n-dimensional cluster algebra, there's an n-dimensional vector associated with it. There's an n-dimensional vector associated with every cluster variable. The initial seed is just the identity, is just the just the basis vectors, and every other cluster variable is written as a linear combination of those guys. For my purpose, what's important is that for every mutation mu, one of these two relations, one of the two relations is actually satisfied by the g vectors and actually determines them. And I'm going to call the set of relations that are satisfied by the g vectors, let me just call them R sub mu. Okay, so for every mutation, one of these two is there, and I'm going to look at the whole collection of them. All right, so that's sort of about cluster algebras and g vectors. How is this related to this picture of kinematic space-time that we just talked about? So, and there's a very beautiful way in which kinematic space-time actually arises from the cluster algebra in a sort of more abstract way. If we consider all of these x plus x minus x minus x type relations, then it turns out there's a tiny subset of them, and this is true for and understood for all the finite type cluster algebras, but let me just start with that. There's a tiny subset of them that actually generates all the rest of the relations by positive linear combination, so that for any mutation, you can write that x plus x minus x relation as a positive linear combination of basic ones. You can think about the basic relations as the pixels or the meshes in this kinematic spacetime. So if I go back to that picture of the kinematic spacetime I have, in fact, I can take any two variables that are the past and the future corners of a causal diamond. There's a relation, there's a mutation relation between any two of these variables, and that relation, it could be big. These variables could be far apart, and that's actually the point, that the relation associated with them is actually a sum of these little basic relations associated with these small meshes. So in this way, the fact that there's a kinematic spacetime is reflecting that not all relations are created equal at the level of the cluster algebra. There's some basic ones that generate all the rest of them. That's an important thing to keep in mind as we try to go beyond finite type, where we're in terra incognita, and we have to be more exploratory about what we're looking for. Now, also before I move on, I want to make a general comment, because I think this is incredibly, to me, it seems incredibly important and interesting, that there's a sort of general connection between something structural about cluster algebras, which is telling us something basic and important about space-time and quantum mechanical processes. If I just stick with tree levels here for the moment, we start with a picture where I have a bunch of propagators, xij, and then I have to put the propagators together in a special way in order to correspond to a space-time process, and then I have to add them all up together because of quantum mechanics and add them all up with +1 in order to get a quantum mechanical amplitude. And so it's our desire to look like a space-time process that tells us to put them together like that, and our desire to be quantum mechanical that tells them to add up in this way. But all of that is actually very natural, and it has a sort of more unified origin from the cluster algebraic point of view. To begin with, every one of these variables is associated with g-vectors, but there's something very beautiful that for every cluster, the g-vectors, there's a little cone associated with all the g-vectors in a cluster. And an amazing fact is that all these cones are actually non-overlapping, and together they tile and cover the whole space. So the fact that there's something special about the space-time process, well, there's something special about these basic cones. The fact that we have to add them all up together, well, it's sort of sitting there in the cluster algebra. We can't take them independently. We can't throw one of them out. They're all touching each other. They touch and tile. And so there's a sort of more unified way in which both the fact that what's interesting are space-time processes and the fact that they're coming up together is reflected in this geometry of the g-vector cones tiling the space. And in fact, the qualitative things of the hidden symmetries and so on that we talked about at the start are really reflected here. For instance, the fact that there's a projectively invariant form, those funny signs that we have to pick are just completely predicted by the determinants of the g-vectors. This is a formula for the form, and I simply take the d log of all these x variables in every cluster, and I weight them with the sign of the determinant of the g-vectors associated with that cluster, and that's guaranteed to be projective invariant. The fact that I can pull back to a subspace means that I have to pull back to a space where I solve for all the other cluster variables in terms of some initial set, and these g's are the g-vectors. And if I do that, you see, when I pull back to the subspace, all the signs go away and I get all +1s. And that happens because not only are these cones are non-overlapping in the tile space, but also very nicely, all these determinants are ±1. So the fact that I get all +1s from the amplitude is reflecting a simple structural fact about the g-vector cones. And finally, if I really, what the whole picture of the kinematic space-time and the ABHY construction is giving you is telling you a canonical way of choosing these constants in defining the subspace, so that what we actually get on the subspace is a polytope with exactly the shape reflecting these cones, where every g-vector is a normal facet to the polytope, and every g-vector cone is associated with one of the vertices of the polytope. So that's extra, that we're going to be talking more about that. But before, the fact that there's a projective invariant form, the fact that we can pull back to a subspace with all the amplitudes being +1 and so on, all of that is sort of structurally built into this fascinating fact about g-vectors non-overlapping and tiling space. Okay, so in this way, we can now that we know this, we can this is true for all finite type algebra. So here's a simple example of a surface cluster algebra, just of a triangulation of a surface with one hole in the middle. You see, these are just a dual of one loop diagrams. On the other hand, the corresponding quivers are just that of the Dn-Dinkin diagrams. All of the finite cluster algebras, the quivers are associated with Dinkin diagrams. And so there's a kinematic space-time associated with this picture. I won't explain this in detail, other than so you can see there's a little Dn-Dinkin diagram sitting there. There are these two nodes or the two antennae of the Dn-Dinkin diagram. But again, the sort of crucial point is that what looks here like a kinematic space-time picture, these basic relations in green also non-trivially generate all of the rest of them. All right, so that was the story that we understood up to one loop. In fact, all the classical algebras A, B, C, D are relevant for amplitudes, tree level for type A, tadpole emission at one loop for type B and C, and one loop for type D. So now what I'd like to talk about is moving to a loop order. And so again, as I just said, trees are associated, an endpoint tree amplitude is associated with the AN -3, Dinkin diagram, the AN -3, cluster algebra, one loop is associated with DN. Starting at 2 loops, for example, here, what you get is the simple quiver. This is actually an affine type D algebra, but already these cluster algebras are infinite. We'll be talking about this infinity now at some length, but it's amusing that we have to deal with this issue of taming the infinity. Not just for n equals 4 super Yang Mills, where we have to deal with the infinity of G4n mod torus that we've heard a lot about, but also for the biadjoint theory, starting at 2 loops and above. And as we'll see, this to me quite strikingly, the same kind of ingredients show up in how we can tame this infinity in this case. Now let me try to describe where this infinity is coming from. The origin of the infinity is simple. So if I think about, let's say, 2 loops, and I draw what the dual diagrams are, this line here is what we normally think of as a loop propagator. However, from the perspective of the surface, and crucial for the cluster algebra, there's not only this line, but there's this line where you wind around the other loop, the other whole once, or you wind around it twice. And in fact, we can wind around an infinite amount in this case. More generally, the infinity is reflecting the action of the mapping class group of the surface. For example, in this case, I can imagine just taking, if I have L loops, I can take the L holes and braid them around each other with an action of the braid group. And that is infinite. Okay? Now, it's also true in the surface cluster algebra case, in general, it's always the case that the G vector cones associated with the cluster variables, they're non-overlapping and they don't have stupid holes in them. They still fit snugly together. In a completely wild cluster algebra, they'll leave a kind of a top dimensional chunk of the space open. In the surface cluster algebra story, quite beautifully, they don't leave any top dimensional holes open, but they do leave lower codimensional holes in the space. What that means is that ahead of time, without thinking, we're guaranteed that there is a projective form. Again, that remarkably, it's possible to choose all these signs so that the projective variation cancels, but the cancellation will be in the form of a telescopic sum that keeps going and going and going, and somewhere eventually you have to pay the price unless you keep on going forever. Okay, so what are we looking for? What we're looking for, we want to somehow, we want to use this remarkable fact that the cluster structure, that the G vector cones are capturing space-time processes. They fit snugly together. We have to add them all up. That's summing overall diagrams because of quantum mechanics. We want to keep all of that, but somehow we want to solve this infinity problem. The infinity problem means we have this crazy infinite covering of the same Feynman diagrams over and over and over again, because from the perspective of the loop variables, these are all exactly the same loop variable. It's from the perspective of the picture on the surface that they keep on winding forever. So are there polytopes where, first, the vertices are unambiguously associated with diagrams or clusters? The G vector, the normal facets are counted amongst the facets of this polytope. It'll give us something projectively invariant, and that there'll be a form associated with it that's projectively invariant. That's trivial, but non-trivial is that we can pull back to the amplitudes with all +1s, which is the requirement that the determinant of all the facet normals in the neighborhood of the vertex are all +or-1. Very non-trivial constraint. Okay, so that's what we're going to be looking for. And now in order to do that, we're going to go back and stare at the kinematic space again, just like we did before. We're just going to stare at the kinematic space. And we'll see that at loop level, this kinematic space-time is richer. And when we just look at the kinematical space-time, we're actually going to find these clusterhedra canonically living there. So I'm just going to go over this relatively quickly, but just so you have an impression of what some of the ideas are. So instead of actually starting at 2 loops, I want to start with another example that doesn't require me to introduce some extra notation and ideas. In fact, I'm going to be talking about an infinite class of cuts. Okay, so an infinite class of cuts at all loop order. Imagine I have endpoints and I have all these loop punctures in the middle, but I'm going to imagine that they're all connected to each other. So my dual diagrams are all connected to each other. So you can think of that as a particular class of diagrams where these cuts necessarily exist. Now, once I do that, the corresponding surface, I might as well just put an annulus in the middle there and make all of these guys. So my surface now is an annulus with n points on the outside and L points on the inside, and that's the space I'm going to talk about. All right, so what are the variables for this surface? Well, first we have what you can think of as these variables that go from the outside to the outside. For example, I can go from I to j, either clockwise or counterclockwise. So xij is not equal to xji. I can go around this inner hole in two directions. I can also have a loop. So we'll call those xii or xii plus n. Those are the out or the in kind of variables. But I also have these variables that can wind around that go from the in to out. So I can start from I and I can wind around as much as I want and go to some capital I downstairs. Finally, there's another very important variable in this story, which is not a cluster variable. It's this variable delta. This variable is just a circle that goes around the annulus. And this is not a cluster variable, but it's a crucial part of the story. And in fact, this delta variable it was also the star of the 4-mass box, of the square roots in the 4-mass box in the n equals 4 story. In the n equals 4 story in that G4A cluster algebra, there's many A11 subalgebras. And the delta is exact, and that's exactly the sort of the subalgebra is the surface algebra with an annulus in the middle, and delta is exactly the relevant and non-cluster variable that showed up in that story. In this context, you see there's something very special about delta. If you look at any sort of skein relation that you get from a chord that goes from the outside to the inside and it intersects delta, you see that in the relations you'll either get a chord that winds one more around in one direction or one more around in the other direction. And at the level of the G vectors, it means that in the direction where the variables are, let's say, winding around positively, then delta is what tells you how to wind one more. So the G vectors will satisfy this relation that x plus w plus delta is x plus w plus 1. And similarly, winding in the opposite direction, they'll satisfy that if you want to wind more negatively, again, you just add delta. Okay, so delta is a very important non-cluster variable in the story. Now, let me give you a picture also, just so you have an idea of what all these G-vector cones and so on look like. And when we saw in the previous talks that the G-vector is asymptote to an interesting direction, you'll see a little more explicitly what that looks like here. This is what happens in this very simple example of the A21 surface. So 2 points on the outside of the annulus, 1 point on the inside. There are 2 kinds of cluster variable A and B that go from the outside in, and there's these loop variables that U and D. And there's delta, which I haven't drawn here, which is, again, the guy that circles around all of them. And I've just drawn what the actual G-vectors look like. Of course, the G-vector, this is a 3-dimensional cluster algebra, so the G-vectors are 3-dimensional vectors, but I only care about the rays in this picture, so I'm intersecting it with some plane in order to draw you a 2-dimensional picture. So here's the ray for U, for D, for A2, B3. On the other side, on the negative side, A minus 1 and B0, and delta is smack in the middle of this picture. Okay, so you see as you go to more winding, everything, all the G vectors start approaching delta. So here's B4, B minus 1, A3, everything starts approaching delta more and more. And here I've shaded in what the various G vector cones look like for the clusters in this picture. So again, all the cones are beautifully non-overlapping. But as you add more and more of them, there's a hole in the space. And as you add more and more of them, the hole closes, but you end up converging to this nice point delta. Another beautiful point is that the positive winding sector is on one side. There's a kind of a plane in the space where all these non-winding variables live. The positive winding guys are on one side of the plane. The negative winding guys are on another side. All right, so now let me sort of summarize what our understanding is for what the clusterhedron looks like in general for this ANL space, for this annulus with n points on the outside and L points on the inside. The first thing we do, as in the previous examples, we just have to stare at what the kinematical space actually is. And once again, there's a space-time picture naturally associated with it. For instance, if I look at the in-out kinematical spacetime, I would want to start with one of these variables. I start, let's say the variable that goes from I to I without winding, then I wind once, twice, 3 times, and so on. Those are all my variables. Well, I can think about getting all of them, starting from any one variable, and just translating by the cyclic action in either one direction or the other. So here I start with the variable that went from point 1 to point 1. Then I cycled from point 1 on the outside boundary to 1 dot on the inside boundary. Then I just cycle 1 dot to 2 dot, 3 dot, 4 dot. And here it's five points on the inside. So it comes back to 1 dot. When it comes back to 1 dot, I wound around once. So there's a winding number increasing in this direction and similarly increasing in this direction. That's it. That's a picture of the kinematical spacetime for these in-out variables. And you see that it's a cylinder because I have an identification between variables on this side and on that, on one side and on the other. So the kinematical spacetime in this case is an infinite cylinder with some natural identification. An important point is that there are actually 2 disconnected cylinders for the sort of winding either in the positive direction or in the negative direction. So that's one kinematical spacetime, and there's already the beginning of something nice happening is that these basic mesh relations that you see in the spacetime positively generate all the other relations that we see with these variables here. So that aspect of the space-time structure that we saw in finite type continues in this case in a quite simple way. What about the in-in and the out-out? In this case, there's no winding. And here it's even simpler to think about then. So I start with a given arc like 1, 2, and I just translate to 1, 3, 1, 4, 1, 5, and then it can come back all the way around to 1, 1. Okay, so here that's what I've done. 1, 2 is 0, right? That's the boundary guy 0. But here's 1, 3, 1, 4, 1, 5, and I come back to 1, 1, and I'm done. And then I just translate everything again. And the whole picture is periodically identified in this direction. So once again, you see the space-time is simply, this kinematic space-time is simply built by starting with a point and acting on it with the cyclic symmetries to produce all the others. Once you do that, again, there are the obvious mesh relations in this picture, and quite nicely, these mesh relations are the basic ones that generate the rest of them. I should pause here to say that this part of the story actually gives a natural home for this beautiful polytope called the halahedron that Giulio Salvatore had found an interpretation for at one loop, but now we see that it has this other purpose in life a little more general. Okay, so these are our space-times. One of them is finite, just looks like a chunk of just a finite chunk. The other one is this infinite cylinder that goes on forever. And now we're going to compactify the space-time. And the idea is very simple. We're just winding more and more and more, but we don't want to keep winding more and more. We want to stop at some point. But how can we stop? The sort of difficulty is that we stop, then there are some relations at the end that we don't have, because there was some winding X, and there was some friend, there was a mutation relation with bigger winding that we don't see. So this relation is missing. And the idea is very simple. Since we know that all that's happening as we go in this direction is we're adding delta, every time you see a variable that winds too much, you just write it as the earlier winding variable plus delta. And the relation that you start with turns into another relation of the form x winding plus delta equals x winding plus 1. So this basic relation involving delta becomes the stand-in for the relations involving the variables that you're missing. In other words, delta is a natural mutation partner for everybody who you've sort of thrown out by doing this compactification. And notice that you only write this relation down at the very end for the guys that are missing, not down here. But all these relations down here are generated by the sort of meshes in the kinematic spacetime, but the ones that you're missing at the edge, you're generating in this way. All right. Next, so now we have these. Now we have this this in-out spacetime with the positive winding and the negative winding. We also have the in-in and the out-out spacetimes, and so clearly there are relations that involve them. So there have to be some way of gluing the in-in to the out-out. The in-in and out-out spacetime to the in-out spacetime, and here the answer ends up being that the simplest possible one, that I take any of the arcs in the in-out spacetime, and I look at the relations they have between this basic loop arc in the in-in. or out-out space-time. So there's some relation of the form x for the loop plus xji for the either biggest winding at the very end of the positive winding space-time or the negative winding space-time. These mesh relations are the basic relations that allow me to glue the space-times together. And finally, the most interesting thing is that there has to be some way of connecting the positive winding and the negative winding regions together. And those are regions that seem completely disconnected from this kinematical space-time picture. So something more interesting has to happen. And once again, delta is the star of the show here. It turns out that there's a completely canonical relation between, for a given kind of variable, just whether it's positive winding or negative winding, there's a totally canonical relation to the form x plus winding plus x minus winding for that single variable with the compatible variables in the dots here, and something involving some positive constant times delta on the right-hand side. So this is quite remarkable that these relations exist, and they allow us to consistently glue the positive and the negative winding spacetimes together. So here's kind of a cartoon of what the final kinematical spacetime looks like in this case. Once again, there is this region with this infinite cylinder. I start from some initial cluster and I just evolve. So I have this in-out kinematical spacetime with positive winding, the in-out kinematical spacetime with negative winding. They're naturally glued, the out-out and in-in. This is just a copy of that out-out. This is just a copy of that in-in. So there are relations here that glue them on one side and glue them on the other side. But most interestingly, delta allows us to glue things on on the positive winding side to the negative winding side. So you can think about the delta as kind of a wormhole that allows me to connect things that are obviously not causally connected in this kinematical space-time picture. Okay, but that's it. That's once you see that the kinematical spacetime consists of these basically three parts: the out-out and the in-in, which are these finite things, and this infinite cylinder. Everything else is following your nose because you have to figure out how to connect them to each other. And the easy part is to see how to connect the in-in and out-out. The somewhat more non-trivial part is to see how you can connect the positive and the negative side, and sort of amazingly, delta allows you to do that. And again, the claim is that now this set of relations in this kinematical spacetime, including this funny wormhole, does indeed positively generate all of the rest of them. And so this picture works for the affine cluster algebra. So we can think of these as affine clusterhedra. Exactly the same ideas work for the affine d tilde algebras, which corresponds to two-loop amplitudes. So we have clusterhedra through two loops, and also at all loop order for this particular class of cups. And just again to summarize, delta is a mutation partner for every missing variable. That means that all the vertices, even the funny vertices that include delta, are actually unambiguously associated with either clusters or with Feynman diagrams. Another very nice fact is that all the vertices not including delta are counted the same number of times. So we're getting sort of, we have to do this evolution on the positive and negative winding side a certain amount. That means that we're getting some number of copies of the loop variables, but we can have as many copies as we like, but we get the same number of all the diagrams. There's no difference between the different diagrams. And finally, another very, very nice fact is that all the normal facets to this polytope, including the ones that include delta, all those normal vectors, the determinants are plus or minus 1. So that means that when we pull back to the substation, we get all plus 1s for the amplitude. So all those things that we wanted for clusterhedra are realized in this case. Let me not go through this in any detail. There's a simple picture of a three-dimensional one, but let me just end. So we're done through two loops, and with some all loop cuts. We're on our way to all loops, and we have a basic strategy. We have to just begin by understanding the kinematic space. Think about the kinematic space, understand what the kinematical space looks like, and we'll see that they divide into naively decoupled topological sectors. Like we saw these different winding sectors, positive and negative winding sectors. We're going to have generalizations of that. And so there should also be naturally in the geometry, there should, as we saw in this example, we should find the analog of deltas that are like wormholes that are allowing to glue these regions together. And let me just flash before ending what the novelty is. It's not just sort of go on higher and higher to higher loops. There's some real novelty that starts at 3 loops and also beyond the planar limit. I should have emphasized earlier, all of this business about the cluster cones fitting and tiling and the projective form and all of that stuff has nothing to do with planarity. So the real novelty, so we can think about these things even beyond the planar limit. But the real novelty, starting at 3 loops and above and also beyond the planar limit, is that the kinematical space is more interesting and looks quote unquote cosmological. So in other words, the variables grow as we do the time evolution. The space-time is growing and the variables grow. For example, the simplest case of a once punctured torus, which is the very beginning of thinking about non-planar corrections. Here, the quiver is the famous Markov quiver, and true to its name, there's a branching process that makes more and more quivers as you go further and further. So we have to deal with that. Actually, in this case, we understand a reasonable amount. There is a clusterhedron for this Markov case, and there is indeed many deltas that allow us to do this compactification. Starting even in the planar limit at 3 loops, we have this issue of not just winding, but we can have all these different interesting braidings as we go from the outside in this example, for instance. And even labeling the arcs is an interesting question. The arcs are labeled by elements of a coset of the braid group here at 3 loops to the braid on 2 of the punctures. And so even labeling these arcs is associated with building words in two letters, A12 and A13. Building those words is you can associate with a tree in this way that again has an exponential growth in what you can talk about, which instead of looking like the Sitter space looks more like false vacuum eternal inflation. In any case, these are the issues that we're now trying to understand, and this is work in progress. All right, okay, so I failed miserably, but I'll stop there. Thank you.
Okay, thanks a lot. Len suggested here that we should be done before the banquet.
Okay, well, we are done.
Or the conference dinner. But yeah, it's not clear in which time zone the conference dinner time is. So we have a couple of questions from Yorgos.
Hi, Nima. I very much enjoyed your talk, and it was an honest and noble effort. So I really appreciate it. It's not about the bed. So my question is, okay, you also elaborated this on Friday. It's a very nice picture, how quantum mechanics comes from cluster algebras, namely that the building block, the Feynman diagram corresponds to a cluster or a cone of the tropical Grassmannian, the tropical geometry. And then the amplitude is a sum thereof in similar way that the whole cluster algebra is made of the clusters, or if the entire tropical fan, yes, is the sum of the cones, which is very appealing and works very nicely at tree level. But then at loop level, you skipped, or you went on and discussed about this annulus with some in points, some out points. But what is the physical picture in terms of the diagrams that you say that you are adding in?
Already we could talk about, I could have paused there longer at 1 loop, but it's sort of what I talked about last year at the Amplitudes. It was in our paper from December. Already at 1 loop, we just have a picture of a disk with a puncture in the middle. And okay, we just draw triangulations of that, and the associated quivers are well, I mean, we know that, so this is a story about the integrand. I forget if I said that explicitly, but this is obviously a story about the integrand. And at tree level, we have all the poles. At 1 loop, we have all the poles involving the loops. And the kind of point is that you know, when you just think about Feynman diagrams, you have this diagram, you have that diagram, you have another diagram, and you're just supposed to add them all up. They have no relationship to each other. You don't care about any relationship that they have to each other. Already at tree level, we see that they have some relationship to each other. For example, this projective invariance, this projective invariance, which is not a property diagram by diagram, only property of the sum of all the diagrams, tells you that this diagram and a nearby one where I can get from one to another by an ST flip, that I have to think about them as being next to each other, right? So the diagrams now get organized in who's close to each other from the perspective of ST flips. The picture of the G-vector cones makes that more explicit, right? I have this cone, I have one that touches it, another one that touches it, and as if I put them together, they can cover the whole space. I didn't emphasize this, but that projective invariance is, I mean, it's really, it's something. You can use it to get new recursion relations, even for these stupid, simple scalar theories that are not, they're not BCFW, they're not other things. It's kind of the analog of dual conformal invariance for n equals 4 superanion mills. You try to make the projective invariance manifest, you get new interesting recursion relations, even for the integrand for tree amplitudes, one loop amplitudes, and to the extent that we can find these polytopes for any loop, if we can find them. So at tree level and at one loop, there's something very simple going on. Starting at 2 loops and above, the novelty is just that while from the perspective of the dual diagram, you would draw sort of one diagram, you draw one, you draw one arc corresponding to a loop. From the perspective of the surface, there are actually many arcs that wind around in some interesting way. And if you only care about the scalar function, the amplitude, you would maybe want to ignore that, you maybe want to identify all of them together, but from the perspective of the form and from the perspective of the underlying cluster structure, you can't do that. They're all there, and for example, the way they all fit to each other, the way the projective invariance works is that when you compute the projective variation of the form, you'd find cancellation of all the diagrams you talked about, but you would push something out to a diagram that now involves a variable that winds around once, and if you kept going, you'd wind around twice, and so on. So you cannot ignore this fact about the underlying surface if you want to manifest these hidden structures. I emphasize this business about the cluster cones just to show that there's something, even before doing anything fancier, there's just something in the story that wants you to put diagrams together in some interesting, non-trivial way that brings out some structures we didn't see, but it's not enough because somehow it keeps on going forever, and you have to be able to stop and compactify the space somehow. I think it's fascinating that what lets you stop and compactify the space are exactly these novel directions that are not cluster variables, this delta thing. And that's exactly the kind of, literally, that delta is literally what we see in the n equals 4 story as the origin of the square roots there. So there too, there is something outside the world of the cluster variables that plays an important role in making things finite. The interpretation of that from the perspective of the Feynman diagrams is a little bit obscure. We don't know what delta means in a Feynman diagram, but interestingly, in this setup, every time delta makes an appearance, it's the mutation partner of somebody that you've thrown out. So even though it doesn't have an official interpretation as a cluster, you can identify every vertex of this polytope involving delta with a certain diagram, only because there's sort of one thing which used to be put in for some other loop variable, winding loop variable that you're replacing with delta. So delta is doing something canonical and interesting in this story to allow you to compactify. Once we get the form, once we get the amplitude, what do we do with delta? That's an interesting question. The most obvious thing to do is to send delta to infinity and to identify all these winding copies. If we do that, we literally get the integrand. Everything is fine. In other words, we literally identify all of these x's with different windings. We just literally make them equal to each other. And then we get the scalar function, which is the integrand. Is there something else that we can do? Is it interesting to keep delta around? Is it good for something? That's a very good question that would be interesting to explore more.
Okay, Lance had the raised hand. You don't want to ask one?
But just to sort of stress the point, all of this, once you get into the mindset that you're going to look at the kinematic space just by plotting the variables, starting with the variable, acting on it with the cyclic symmetry to fill out this space, which gives you a notion of locality, of what variable is close to what other variable, depending on how much you have to cyclically rotate to get from one to the other. Once you start with that notion, you get a notion of locality in this kinematic space. It tells you what the basic relations should be. Then the rest is just sort of forced on you. You have to sort of keep on going and see what makes sense. The non-trivial part is that these relations are actually consistent. It's not at all obvious that the sort of wormhole that lets you connect positive and negative winding gives you consistent relations with all the rest of them. And it's certainly not obvious that this whole set of relations positively generates all the other relations of the cluster algebra. That was already a sort of a beautiful fact in finite type, and it seems to continue to be the case here. So I think this is all pretty exploratory. These are not canonical polytopes from the perspective of cluster algebras. This is some way of making a finite polytope associated with infinite type cluster algebras, which uses in a very important way these non-cluster variables. And well, we'll see what the ultimate conceptual underpinning is. But this idea that there are chunks of relations that have this local interpretation of a certain kind of kinematic space-time seems to be at least one of the guiding principles behind what's making this work.
Thank you. It's just that it's so appealing, the picture that you draw, that yes, the three-level diagram corresponds to the triangulation, yes, of a polygon. That's why, since we have this beautiful picture at three level, it would be awesome if something like this could also hold at loop level and delta would make an appearance. I think it's a natural question to ask. And perhaps it's also this notion of nearness that you mentioned. I think for three level, it has to do with taking the limits, consecutive limits, like one way and the other. So I guess maybe the infinity is that this, yes. This,
and it's also related to collinear and soft limits here, of course, right? Because things that are near, you can sort of collapse on top of each other. I mean, again, since we don't know what the most primary idea is here, I was trying to present some both the sort of G-vector way and the kinematical space-time way of thinking about what is going on. The non-triviality is the fact that they match. Yeah, we'll see what ends up being the more primary idea. What I want to say is that you would have a desire somehow from this picture to connect positive and negative, and a desire to be able to end. And delta is doing like double duty to allow you to do both of those things at the same time. So even though it doesn't have an official interpretation as a loop variable, it certainly has a sort of very natural purpose in life from this point of view.
So Lauren has a question.
Yeah, thank you very much. I was wondering, do you know or do you expect that there's a clusterhedron for any surface with punctures and marked points?
That's what we hope. Yeah, that is what we hope. Because that's what you'd want for amplitudes for the biojoint theory at all loop order and at all orders in the one-to-round expansion. That's what we're after. Okay?
And
so that's what we're hoping.
And I guess the related question is there a physical interpretation, or you expect there will be one for any surface?
Yes, absolutely, absolutely. Yeah, planar is just a leading order in the one-to-round expansion. Again, so the first step beyond finite is clearly affine, and that we have under pretty good control. And then, there is this fact, you know very well, that's what I was saying at the very end, that there is a sort of exponential explosion in the rate at which cluster variables grow, and that means that our variables are sort of cosmological, and we really see that very concretely in this Markov example. So it's not a trivial thing to go from the affine case to the generic case. So there is something really new that happens, and that's really what we're studying now to try to figure out how to make sense of that. We understand it pretty well in Markov. We'd like to understand it a lot more generally.
Mm-hmm. Thank you.
Okay, going back to Lance.
Hey Nima, great talk. Can't claim I understood it all, but could you say briefly, have you thought about what it would look like in string theory as opposed to field theory, where you mod out by the mapping class group and stuff like that?
Yeah, I'll tell you that, you know, and I actually mentioned this at Amplitudes last year. For a year and a half, Julio and Hadley and I, before we started talking to our cluster friends more, just thought all we had to do was quote unquote mod out by the mapping class group, which meant just make some dumb identification. Oh, this thing is winding around, just identify. So this equals that, right? And you know, it works for a few examples, and then you just keep hitting brick wall after brick wall after brick wall. So somehow what we're doing is modding out by the mapping class group, but not by literally making an identification, but by keeping like as many copies as we want and then stopping somehow. It just is not the literal modding out idea. We're too much in the middle of it now, so I don't want to speculate too much more because it's clear that we don't really deeply understand what is going on here. So I don't know in the end whether it'll be something essentially different than modding out or a little sort of decoration on top of the idea of modding out. But in any case, it's not literally modding out. Literally modding out would have been say, oh, the variables are just equal, forget it, right? Or just they're different in some stupid, obvious way, and that just does not work. It runs into various problems, even doing something as basic as making this form projective. You really appreciate the magic that I was mentioning about the cluster codes fitting and all that stuff when you forget about it, which is what we were doing, partially because at least I didn't know it. And then you just try to do it by hand. You know, make this sign, that sign, that sign. And then you spend all this enormous amount of time and you find some example that works and then you think it'll generalize and it doesn't generalize. The thing that just works on the nose is taking the G vectors that come out of the cluster algebra. So you don't want to fuck with those. But somehow just doing that is not enough and you have to close up the space somehow. How it's related to what we do in string theory, I don't know. And there's a very obvious question. What happens to the stringy canonical? We can talk about a stringy canonical form now with any of these examples. We know what to do. Now we just keep on going. We include delta. We write all the variables in terms of the initial cluster. We write down a stringy canonical form. So there's some kind of stringy canonical form that we can talk about at two loops, all these examples. What do they mean? We have no idea. As a generalization of what we have no idea what they mean, even for the one loop DN case. But yeah, so I'm sorry I don't have a better answer to your question, but it's certainly, the idea of trying to mod out is what we began with, and we really, with a lot of prodding and failure, moved to this other idea.
Thanks.
Okay, more questions? Okay, there are some, there are two more questions. Azadeh Malekneyat.
Yeah, hi. Thank you very much for the fabulous talk. I have a very basic question for you. So the G vectors are simply the roots of the algebra who lives in the Cartan subspace, right?
In the finite type, they're related to that. But I think that for this purpose, the simplest way to think about what they are, in all those cases where we have these nice polytopes, just think of them as the normal vectors to the faces of the corresponding polytopes.
So the reason that I'm asking that is just because I'm trying to understand delta. So So my understanding is that when we classify the simple Lie algebras or semi-simple Lie algebras is based on finding SU2 sub-algebras and then composing everything in terms of like Hermitian operators are the Cartan sub-algebras, and then the raising and lowering operators which are anti-Hermitian.
It's not, I mean, it's, of course, there are root systems associated with these quivers, but that's not exactly what the G vectors are. I can tell you, I mean, in fact, I think you were at my lectures on Friday, and we spent about an hour and a half talking about cluster algebras and G vectors at that lecture. So I'd be happy to talk about it more offline if you want to chat about it more.
Okay, to move on, David.
So with your permission, Yaroslav, I'd like to address my question first to Marcus because his question time was taken up.
Marcus around?
I am here, yes.
Thank you. So the three main differences I see between super Yang-Mills and the realistic field theories of the standard model are we have a coupling constant that runs, we don't have a finite circle of convergence. We don't believe we have, and we're not restricted to multiple polar logarithms. Which of those three obstacles, if any, do you regard as difficult, and which might be overcome?
Well, that's too broad a question for such a forum, because I mean, the whole set of ideas that's under discussion here spans such a broad range. So various things are easily generalized, say, to less supersymmetric or non-supersymmetric Yang-Mills theory, while other things that are under discussion are very specifically tied. So okay. Maybe we should talk about that later. Nima, do you want to weigh in on that?
Well, just to say that at least it seems naively, there isn't anything super qualitatively different, other than that eventually it takes longer to see genericity, but we're not restricted to multiple poly logarithms, even at n=4 super Yang-Mills. But instead of seeing them early on in the in the sunrise diagram with masses, you have to have enough external legs involved so that you get something effectively massive inside the diagram. So we've got to go to 10 point, 9 point, beyond n squared mh3, n cubed mh3, maybe before we start seeing those things. So I don't see any. I mean, maybe other people are definitely more expert than me, but I don't see anything ultimately very different than the kind of numbers and the class of functions that are going to show up, because naively, intuitively, deep inside a big loop diagram, you don't really know where it's going to end on the outside and all that stuff. It's something you know much better than I do, David. Yeah, so I don't see anything. I think the biggest qualitative difference, but that's not so much about n=4, it's just about planarity. Planarity lets us have a finite radius of convergence for the 't Hooft expansion, and so perturbation theory is an outstanding guide to the non-perturbative physics. And one of the funny things is someone who has not done these very difficult, amazing calculations using integrability and other methods to get finite coupling results that are so stunning. But it is kind of amazing in the end. In planar theories, every function you draw after having done all this hard work just looks like this. Super smooth functions, not much happening as you go from g of 0.1 to g of 3, right? They're not doing much. And that's, of course, very different between planar theories and theories at finite n, where more genuinely non-perturbative things, more generally excitingly non-perturbative things happen. So that's the thing which is the missing. But yeah.
Thank you.
Okay, any more questions for Nima or Mark? No. Okay, so let's thank Nima and Mark again. And
thank you for your forbearance too. Thank you. I'll be happy to pay off any bets.
Okay. And yeah, so this is officially the end of today's session. So I guess the recording stops